Far out in the universe lies a star so colossal that words like giant or massive fail to capture its scale. This star is Westerlund 1-26, a true monster in the cosmos. It is not just another bright point in the night sky. It is one of the largest stars ever discovered, a red supergiant so immense that it challenges our very understanding of what a star can be. Its existence is a reminder that the universe holds powers beyond human comprehension, forces so vast and destructive that they make even our sun seem small and fragile by comparison. Westerlund 1-26 doesn't float alone in the void. It is part of a dense and extraordinary stellar family known as the Westerlund 1-star cluster. Located roughly 14,000 to 16,000 light-years from Earth in the constellation Ara, this cluster is one of the most massive young star clusters in our galaxy, containing hundreds of high-mass stars packed into a relatively small region of space. Westerlund 1 itself is obscured from naked eye observation due to thick clouds of interstellar dust, making it virtually invisible without the aid of powerful telescopes that can peer through the murky veil. Within this cluster, Westerlund 1-26 stands out not only for its staggering size, but also for its brilliant luminosity, which dominates the light emitted from its neighborhood despite being so far away. Being part of such a massive cluster has profound implications for the star's evolution. Interactions with neighboring stars, gravitational influences, and the cluster's high-density environment all contribute to the star's behavior, including its rapid mass loss and the violent stellar winds it emits. The cluster itself is a cosmic laboratory, giving astronomers a unique opportunity to study how some of the most massive stars in the universe live, evolve, and eventually die. Even though it is tens of thousands of light-years away, the light from Westerlund 1-26 carries secrets of extreme stellar physics, the kind of forces and processes that cannot exist in smaller stars. Its hiding place within this cluster is both a protective cocoon and a dramatic stage for one of the universe's most awe-inspiring giants. When astronomers began comparing Westerlund 1-26 to other well-known stellar titans, its true magnitude became impossible to ignore. UY Scuti, often celebrated as one of the largest stars previously known, has an estimated radius around 1,700 times that of our Sun. UY Canis Majoris, another legendary red supergiant, measures roughly 1,400 times the Sun's radius. At first glance, these numbers are already mind-boggling, capable of swallowing the inner planets of our solar system without effort. Yet Westerlund 1-26 surpasses them in ways that stretch the limits of comprehension. Its radius, estimated at over 1,500 times that of the Sun, positions it among the most colossal stars ever documented, and when factoring in uncertainties in measurement, it could rival or even exceed UY Scuti in sheer volume. The comparison becomes even more striking when we move from abstract numbers to visualizing these giants within a familiar context. If UY Scuti or UY Canis Majoris replace the Sun, their outer layers would extend past the orbit of Jupiter, swallowing Mercury, Venus, Earth, Mars, and potentially beyond. Westerlund 1-26, however, has the potential to extend even further, making the notion of planets orbiting nearby almost meaningless. They would be obliterated long before they could exist. Its mass and energy output dwarf these other giants, emphasizing that Westerlund 1-26 is not just bigger in a casual sense. It occupies a realm of stellar gigantism that is rarely witnessed. In a universe where size and power vary dramatically, this star stands as a behemoth, a cosmic heavyweight that challenges the way we visualize the extreme limits of stellar evolution. The sheer size of Westerlund 1-26 is almost impossible to grasp with everyday intuition. Its radius is estimated to be over 1,500 times that of our Sun, which is already a colossal reference point. To put this into perspective, if you were to replace our Sun with Westerlund 1-26, the star's surface would extend well past the orbit of Jupiter, swallowing Mercury, Venus, Earth, Mars, and even the gas giant itself. The inner solar system, as we know it, would cease to exist entirely. Planets, moons, and asteroids alike would be consumed in its blazing, turbulent envelope. Its size is so vast that even light takes a noticeably longer time to traverse its radius, unlike smaller stars where the transit of light is almost instantaneous. But the enormity of Westerlund 1-26 isn't just a curiosity, it has profound implications for its life cycle. The larger a star becomes, the more unstable it tends to be. With such an immense volume, the outer layers are loosely bound by gravity, prone to shedding in massive stellar winds that can eject material at millions of kilometers per hour. This process is part of what makes the star not only enormous, but also exceptionally violent in its final stages. Visualizing a star that could engulf the entire inner solar system challenges our understanding of scale, highlighting how the universe can construct objects so large that they dwarf entire planetary systems. Westerlund 1-26 is not merely a star, it is a sprawling cosmic furnace, a reminder of the mind-bending extremes nature can achieve. Westerlund 1-26 is so vast that trying to compare it to our Sun begins to feel almost absurd. While the Sun itself is a massive sphere of plasma, the sheer volume of Westerlund 1-26 is staggering by comparison. Estimates suggest that over 10 million suns could fit inside this single star if it were hollow, a mind-boggling figure that underscores just how incomprehensibly massive it is. This is not a metaphor or exaggeration. The numbers come from simple, volumetric calculations based on its estimated radius, and they highlight the extreme scale at which some stars operate. To think about it in another way, if you could somehow place our Sun within Westerlund 1-26, it would be a tiny, almost invisible speck buried deep within the colossal star's outer layers, dwarfed in size by its immense radius. The consequences of such size go beyond just volume. The star's gravity, energy output, and instability are all amplified by its enormity. With so much mass concentrated in one object, the internal pressures and temperatures reach levels that are almost impossible to imagine. Nuclear fusion, the process that powers stars, occurs at incredible rates in such giants, burning through fuel at a pace that would make smaller stars like the Sun seem lethargic in comparison. The core becomes a cauldron of violent reactions, producing energy that radiates outward to the star's enormous surface, creating stellar winds that can eject material equivalent to multiple suns over relatively short periods. Westerlund 1-26 is not just larger, it is fundamentally more extreme. A star whose scale reshapes our understanding of what a single celestial body can contain and achieve. Westerlund 1-26 is classified as a red supergiant, a title that immediately signals both its size and the extraordinary stage of life it occupies in the cosmos. Red supergiants represent one of the final phases in the evolution of massive stars, a period marked by extreme expansion, instability, and prodigious energy output. Unlike stars like the Sun, which spend billions of years burning hydrogen in a relatively stable state, red supergiants have exhausted the majority of their hydrogen fuel in the core and are now fusing heavier elements in successive layers. In the case of Westerlund 1-26, this process has caused the star to swell to over 1,500 times the radius of the Sun, its outer envelope puffed up to a size that defies human imagination. The enormous surface area and relatively cool temperature compared to smaller, hotter stars give it a deep red hue, making it an unmistakable giant among the stellar population. The red supergiant phase is both dramatic and precarious. As stars expand, their outer layers become increasingly tenuous, held only loosely by gravity. This makes them highly unstable, prone to losing mass through massive stellar winds that can expel material at millions of kilometers per hour. For Westerlund 1 to 26, these winds are not minor breezes. They are torrents capable of shedding the equivalent of multiple suns over the course of tens of thousands of years. This mass loss has a direct impact on the star's ultimate fate. The more material it loses, the different its collapse and supernova will be, potentially influencing whether it forms a black hole or a neutron star. Essentially, the red supergiant stage is a race against time, a period in which the star teeters on the edge of cosmic disaster while simultaneously shaping the elements and structure of its surrounding environment. Red supergiants like Westerlund 1-26 are rare. The extreme mass required to reach this phase means that few stars ever become red supergiants, and fewer still reach the gargantuan size of Westerlund 1 to 26. These stars live fast and die young, burning through their fuel at a catastrophic pace compared to smaller stars. While our Sun will last about 10 billion years, a red supergiant like Westerlund 1-26 has a lifespan measured in just a few million years, a fleeting existence in astronomical terms. Their brevity is part of what makes them so fascinating. They are like cosmic fireworks, massive, brilliant, and inevitably heading toward an explosive end. The life of a red supergiant is therefore a story of extremity, where size, energy, and instability converge in ways that test the very limits of astrophysical theory. The classification of Westerlund 1-26 as a red supergiant also highlights its role in the life cycle of matter in the universe. These stars act as cosmic forgers, synthesizing heavy elements like carbon, oxygen, and iron through nuclear fusion in their cores. When they eventually explode as supernovae, these elements are scattered across space, enriching interstellar clouds and providing the building blocks for new stars, planets, and potentially life. In this sense, Westerlund 1-26 is not only a destructive force, but also a creative one, seeding its galaxy with the fundamental ingredients of the cosmos. Its existence underscores the duality of massive stars. They are both catastrophic and generative, capable of unimaginable devastation, while simultaneously giving rise to the very matter that makes up galaxies, planets, and living beings. The physical conditions within a red supergiant are equally extraordinary. The core temperature of a star like Westerlund 1-26 can reach hundreds of millions of degrees Kelvin, enabling the fusion of increasingly heavier elements. Layers of helium, carbon, neon, oxygen, and silicon form concentric shells around the core, each undergoing fusion reactions at breakneck speed. This layered structure is analogous to an onion, but one where each shell produces more energy than the sun emits in an entire year. Meanwhile, the outer layers remain comparatively cool, giving the star its signature red coloration, but they are constantly buffeted by shock waves and convection currents that carry energy outward. The dynamics of these layers are so intense that they can trigger massive pulsations in the star's radius, causing it to expand and contract over time. Observations of Westerlund 1-26 suggest that its outer envelope is not smooth but irregular and turbulent, evidence of the immense forces at play within a star of this magnitude. One of the most fascinating aspects of red supergiants like Westerlund 1-26 is their unpredictability. While astronomers can estimate a star's mass, radius, and likely lifespan, the precise timing and nature of its ultimate collapse remain uncertain. This is partly due to the complex interactions between radiation pressure, gravity, and nuclear reactions within the star's interior. Any sudden instability in one layer can propagate through the star, potentially triggering eruptions that eject enormous amounts of mass. These outbursts are not minor events. They can rival the energy output of entire galaxies for brief periods. For Westerlund 1 to 26, such violent behavior is a harbinger of its eventual supernova, a cataclysm that will mark both the end of the star and the beginning of a new cycle of cosmic evolution. Despite its immense distance from Earth, about 14,000 to 16,000 light-years away, the study of Westerlund 1-26 offers invaluable insights into stellar physics. Observations using infrared and radio telescopes have allowed astronomers to penetrate the dense dust of the Westerlund 1 cluster, revealing not just the star itself, but also the dynamic environment it inhabits. Surrounding Westerlund 1 to 26 are numerous other massive stars, many of them in similarly extreme stages of evolution. The interplay between these stellar giants, through radiation, gravity, and stellar winds, creates a uniquely energetic region of space. Westerlund 1 to 26, however, remains the dominant force, a leviathan whose influence shapes the cluster in profound ways, from triggering star formation in nearby clouds to enriching the interstellar medium with heavy elements lost through its winds. The red supergiant phase is also a stark reminder of the impermanence of even the most massive celestial bodies. Stars like Westerlund 1 to 26 live fast, radiate enormous energy, and ultimately face catastrophic ends. Their existence is a study in extremes: extreme size, extreme luminosity, extreme instability. In observing Westerlund 1-26, astronomers are confronted not with the calm permanence of smaller stars, but with the raw, violent processes that govern the life cycle of the universe's giants. Every observation of this star provides a window into forces and scales that defy ordinary comprehension, from the turbulent convection currents churning its surface to the nuclear furnaces burning deep within. In every sense, Westerlund 1 to 26 embodies the dramatic, awe-inspiring, and terrifying aspects of cosmic evolution. Westerlund 1-26 is not just a giant in size. It is a star racing toward its ultimate demise, burning through its remaining fuel at a rate that is nothing short of catastrophic. Unlike smaller, more stable stars like our Sun, which convert hydrogen into helium steadily over billions of years, a red supergiant of this magnitude exists on borrowed time. Westerlund 1 to 26 has long since exhausted the hydrogen at its core and now relies on a series of complex fusion processes, burning helium, carbon, neon, oxygen, and even heavier elements in concentric shells. These nuclear reactions occur at exponentially higher rates than in smaller stars, generating enormous amounts of energy and driving the star into an unstable, turbulent state. The pace at which it consumes its fuel is so extreme that every second brings it closer to the dramatic and violent end that all red supergiants inevitably face. The core of Westerlund 1-26 is effectively a cosmic pressure cooker, where temperatures soar to hundreds of millions of degrees Kelvin. At these extremes, matter behaves in ways that are nearly impossible to replicate or fully comprehend on Earth. The nuclear fusion reactions occurring in the core release immense energy, creating outward pressure that balances the inward pull of gravity. Yet, in a star of this size, even slight imbalances can have dramatic consequences. The outer layers, loosely held by gravity due to the star's enormous radius, respond to the turbulence of the interior with violent pulsations and massive ejections of stellar material. These processes are not sporadic, they are constant, signifying a star that is actively deteriorating as it burns through its remaining life. This accelerated fuel consumption is a defining characteristic of massive red supergiants. While smaller stars may linger for billions of years, Westerlund 1-26's extreme mass ensures a far more fleeting existence. Every million years in the life of this star represents a rapid progression through stages of stellar evolution that would last much longer in less massive stars. Its instability is mirrored in its luminosity, which can fluctuate significantly as the star pulsates, shedding outer layers and emitting powerful stellar winds. Astronomers have observed signs that Westerlund 1-26 is already undergoing significant mass loss, a clear indication that its days are numbered and that it is steadily approaching the point of no return. The catastrophic pace at which Westerlund 1-26 burns fuel also contributes to its enormous energy output. The star radiates light and heat at levels so extreme that it can outshine entire star clusters. In a single second, it emits more energy than our Sun will produce over an entire year. This relentless output is a direct consequence of the high fusion rates in its core and the immense surface area over which this energy is released. The combination of extreme luminosity, massive size, and violent instability makes Westerlund 1-26 a textbook example of the incredible forces at play in the final stages of stellar life for the most massive stars. Even the outer envelope of the star, the part we see from Earth, is affected by the chaotic energy from the core. Convection currents carry heat and radiation outward, creating turbulent zones on the star's surface. These zones can produce localized eruptions, sending massive amounts of gas and plasma hurtling into space. The material lost in this way doesn't just vanish, it becomes part of the interstellar medium, enriching the surrounding space with heavy elements that will eventually contribute to the formation of new stars and planets. Westerlund 1-26, in this sense, is both a dying giant and a cosmic creator, shedding matter as it marches inevitably toward collapse. The star's current stage is a vivid reminder that even the largest and most powerful objects in the universe are not eternal. The colossal fusion reactions inside Westerlund 1-26 are pushing it ever closer to instability, a tipping point at which the core can no longer support the immense mass pressing down upon it. When this occurs, the star will collapse under its own gravity, leading to one of the most energetic events imaginable, a supernova. This is the final act in the life of a red supergiant, and for Westerlund 1-26, it is approaching with an inevitability that is both awe-inspiring and terrifying. In essence, the light we see from Westerlund 1-26 is not just illumination. It is a signal of a star in its death throes. Each photon, radiating across 14,000 to 16,000 light-years, tells the story of extreme energy, instability, and impending catastrophe. The star is a living demonstration of cosmic impermanence, burning brightly and violently as it prepares for the ultimate collapse. Its catastrophic pace of fuel consumption makes it one of the most compelling laboratories in the universe for understanding the life cycle of massive stars, offering glimpses into processes that will ultimately shape galaxies and influence the cosmic environment long after the star itself ceases to exist. Westerlund 1-26 is not only a monument to size and mass, it is a cosmic furnace of unimaginable power, radiating energy on a scale that defies normal comprehension. While our Sun produces a staggering 3.8 times 10 to the 26th watts of energy each second, Westerlund 1-26 emits many millions of times more energy than that in the same period. In fact, estimates suggest that in just a single second, this colossal star radiates more energy than the Sun will over its entire 10 billion year lifetime. The intensity of this output is staggering. It is not merely bright, but an incandescent furnace radiating across the electromagnetic spectrum from visible light to infrared, with far-reaching consequences for its surrounding environment. Observing such a star is like peering at the concentrated fury of billions of suns condensed into a single object, a reminder that the universe can generate energy on scales that are almost impossible for the human mind to truly visualize. The mechanisms behind this extreme energy output are tied directly to the star's massive size and the rapid rate of nuclear fusion occurring in its core. Within Westerlund 1 to 26, layers of nuclear fusion produce heavier and heavier elements in a cascading series of reactions, from helium to carbon, oxygen, and even elements as heavy as silicon. Each of these fusion reactions releases vast amounts of energy in the form of gamma rays, neutrinos, and thermal radiation, which then push outward through the star's enormous envelope. The convection currents in the outer layers distribute this energy unevenly, creating pulsations and surface turbulence that amplify the star's instability. This turbulence is visible as irregularities in brightness when observed from Earth, subtle hints of the colossal forces at work beneath the red surface of the supergiant. The stellar winds, produced by Westerlund 1-26, are another key factor in its role as a cosmic furnace. These winds, driven by radiation pressure and the violent dynamics of the star's outer layers, blow material outward at millions of kilometers per hour. They carry both energy and mass into the surrounding interstellar medium, creating a zone of heated plasma that interacts with nearby stars and interstellar clouds. This ejected material, enriched with heavy elements, acts as a catalyst for star formation in the region, highlighting how a dying star can simultaneously act as a creative force within its galaxy. The energy it radiates is not confined to light. It manifests as heat, kinetic energy in the expelled matter, and ionizing radiation capable of altering the chemical composition of nearby cosmic clouds. In this way, Westerlund 1-26 is both a furnace and a forge, transforming the surrounding space while accelerating its own demise. Comparing its luminosity to the Sun or other stars only hints at the true scale of its power. If our Sun were placed at the center of Westerlund 1-26, it would appear as a small, dim point of light against the backdrop of the star's immense surface. The radiative output of Westerlund 1-26 is so extreme that even at distances of tens of thousands of light-years, it significantly affects the thermal and radiative balance of the cluster it inhabits. Light from the star interacts with interstellar dust and gas, heating the environment and creating dynamic conditions that shape the evolution of its star cluster. In essence, Westerlund 1-26 acts as a central powerhouse, radiating both energy and influence outward in ways that smaller stars could never achieve. The star's energy output also underscores its instability and rapid evolutionary pace. As Westerlund 1-26 fuses heavier elements at breakneck speed, the enormous pressure and temperature within its core produce energy that strains the star's structure. Its outer layers, tenuous and vast, respond with violent pulsations and frequent mass ejections. Each of these events releases energy comparable to millions of suns, contributing to the overall luminosity while simultaneously accelerating the star's approach towards supernova. In a sense, the energy output of Westerlund 1-26 is both a symptom and a driver of its death. A self-propelling cycle of energy release, instability, and gradual disintegration of the star's outer envelope. Even the light that reaches Earth carries a story of incomprehensible magnitude. Traveling over 14,000 to 16,000 light-years photons from Westerlund 1-26 provide astronomers with data not only on its current state, but also on processes that occurred millennia ago within its roiling interior. The intensity of its radiated energy allows telescopes to detect subtle fluctuations in brightness, offering insights into the complex dynamics of the star's outer layers and the convective currents beneath. Every observation confirms that this is not a passive giant, but a violently energetic entity, a furnace whose heat and light illuminate not only the cluster it resides in, but also the boundaries of human understanding of stellar physics. Westerlund 1-26's role as a cosmic furnace extends beyond its immediate surroundings. By injecting energy and material into the interstellar medium, it drives processes that can influence star formation across vast regions of its galaxy. The expelled matter, enriched with heavy elements, contributes to the cosmic chemical cycle, ensuring that subsequent generations of stars and planetary systems carry the signatures of this ancient and immense stellar powerhouse. In this sense, the energy of Westerlund 1-26 is both destructive and generative. It obliterates the immediate stability of its outer layers, while fostering conditions that allow new celestial structures to emerge. Its brilliance is a testament to the incredible forces that govern the lives of the universe's most massive stars, a constant reminder that even in death, a star of this magnitude shapes the cosmos in profound and lasting ways. The cosmic furnace of Westerlund 1-26 also provides a preview of the cataclysmic events yet to come. Every photon, every particle of ejected mass is a small warning of the supernova that awaits. The immense energy it radiates today is a prelude to an even more violent release in the near-cosmic future. This energy not only illuminates its surroundings but also stirs the imagination, prompting humans to confront scales and forces far beyond terrestrial experience. To witness or even study such a furnace is to stand at the edge of comprehension, gazing at a star whose power makes our sun look almost quaint in comparison, and whose eventual demise promises an explosion of energy that will dwarf anything our solar system could produce. Westerlund 1-26 is a star living on borrowed time, a colossal giant whose very existence teeters on the edge of cosmic instability. Unlike smaller, more stable stars, such as our Sun, this red supergiant's enormous mass and bloated outer layers make it inherently unstable. Its surface is not a calm, steady shell of plasma, but a turbulent, constantly shifting expanse, buffeted by immense convection currents and violent pulsations that arise from the seething furnace at its core. These instabilities manifest in one of the most dramatic and consequential behaviors of the star. It is shedding mass at a staggering rate through powerful stellar winds. These winds are not the gentle breezes of ordinary stars. They are torrents capable of ejecting the equivalent of multiple suns' worth of material into space over a relatively short period, fundamentally altering the star's structure and accelerating its inevitable demise. The process of mass loss in Westerlund 1-26 is intimately connected to both its size and its evolutionary stage. As a red supergiant, its outer layers are loosely bound by gravity because of the star's enormous radius, sometimes extending beyond the orbit of Jupiter if it were placed in our solar system. This tenuous outer envelope is easily disrupted by internal instabilities, allowing matter to escape into space in waves of stellar wind that can reach hundreds or even thousands of kilometers per second. These ejections are not uniform. They occur in clumps and bursts, producing massive outflows that form an expanding cocoon of gas and dust around the star. Over time, this material contributes to the enrichment of the interstellar medium, seeding future stars and planets with the heavy elements forged in the star's core. In essence, while Westerlund 1-26 is dying, it is also leaving a legacy that will shape the chemical and physical environment of its galaxy for millennia to come. The mass loss has a profound effect on the star's life expectancy and ultimate fate. Every kilogram of material ejected reduces the gravitational pressure on the core, which can slightly alter the internal fusion rates and the structure of the star's layers. However, this is a double-edged sword. While shedding mass can temporarily relieve pressure, it also destabilizes the delicate balance that allows the star to maintain its enormous size without collapsing. The outer layers, already extended and fragile, are continually buffeted by turbulence and radiation pressure from the core, leading to further pulsations and mass loss in a vicious cycle. For a star of this magnitude, such processes are not minor inconveniences. They dictate the timing, scale, and character of the cataclysmic end that awaits. Observations of Westerlund 1 to 26 show that the expelled material forms a complex circumstellar environment with layers of gas and dust moving outward at incredible speeds. Infrared and radio telescopes have detected these vast clouds, which glow as they are heated by the star's extreme radiation. The patterns in these outflows suggest violent eruptions and sporadic bursts of mass loss rather than a uniform, steady process. This indicates that the star's interior is far from stable. Shock waves and convective turbulence from the core propagate through the outer envelope, ejecting matter in massive, sometimes unpredictable events. Each ejection changes the balance of forces within the star, subtly shifting the dynamics of the remaining mass and hastening the approach of the supernova stage. The stellar winds of Westerlund 1-26 are not only a signal of instability, they are a reminder of the star's enormous destructive potential. The mass being expelled carries kinetic energy equivalent to millions of suns interacting with nearby gas, dust, and stars, shaping the environment of the Westerlund 1 cluster in dramatic ways. Over thousands of years, these winds can carve cavities in surrounding molecular clouds, trigger new star formation, and redistribute the heavy elements synthesized in the star's core. In this sense, the star's instability is not merely a sign of decay, it is also a mechanism through which it continues to influence the cosmos, even as it nears the end of its life. Despite the beauty of the glowing clouds and the creation of new material, the picture is also one of impending doom. Westerlund 1-26's rapid mass loss indicates that it is approaching a tipping point, a stage where the core will no longer be able to support the immense weight of the remaining outer layers. When that happens, gravity will take over in a catastrophic collapse, leading to one of the most energetic events imaginable, a supernova. The star is effectively ticking down a cosmic clock, each pulsation, each wind-driven ejection, a reminder that time is running out. Its life is a fleeting, dramatic blaze of energy and instability, a cosmic spectacle that both illuminates and disrupts the space around it. The instability of Westerlund 1-26 is also a window into the processes that govern the lives of all massive stars. By studying its mass loss and the behavior of its stellar winds, astronomers gain insight into how red supergiants evolve, how they prepare for supernovae, and how they enrich the universe with heavy elements. Every observation is a piece of a puzzle that helps scientists understand the interplay of gravity, radiation, and nuclear fusion at the larger scales. Westerlund 1-26's violent instability is not an anomaly. It is a natural consequence of its extreme size and evolutionary stage, a star living on borrowed time, yet simultaneously shaping the cosmos in ways that will outlive it. Living on borrowed time, Westerlund 1-26 is a reminder of both the beauty and danger inherent in the universe. Its stellar winds are a testament to the forces unleashed by extreme mass and instability, a process that destroys as it creates. Every particle of gas expelled carries energy, mass, and information, contributing to the ongoing evolution of its galactic neighborhood. It is a star in the most dramatic sense, a colossal, living furnace teetering on the edge of destruction, its instability both a harbinger of doom and a generator of cosmic renewal. The life of Westerlund 1-26 is a fleeting, violent phenomenon, a window into the raw, unrelenting power that governs the universe's most massive objects. As Westerlund 1-26 hurtles toward the end of its life, the inevitable question arises: what will happen when this colossal star can no longer support its own mass? The answer lies in one of the universe's most extreme and awe-inspiring phenomena: gravitational collapse. Once the star exhausts the last of its nuclear fuel, the delicate balance between radiation pressure pushing outward and gravity pulling inward will vanish. Without the outward pressure generated by fusion to counteract the crushing weight of its own mass, the core will collapse in an instant, setting the stage for a cataclysmic supernova. The outcome of this collapse depends largely on the mass of the remaining core and the dynamics of the ejected outer layers, and for a star as massive as Westerlund 1-26, the possibilities are as terrifying as they are fascinating. If the core is massive enough after the supernova explosion, it will compress into a black hole, an object so dense that not even light can escape its gravitational pull. The black hole formed from Westerlund 1-26 would be a stellar mass black hole of extraordinary size, likely exceeding tens of solar masses, and it would serve as a lasting testament to the star's incredible original mass. Such a black hole would warp space-time in its vicinity, producing gravitational effects detectable across vast distances, and potentially pulling in nearby gas, dust, or even smaller stars over time. The creation of a black hole from Westerlund 1-26 is not just an ending, it is a transformation of matter and energy into a state of pure gravitational dominance, an object that embodies the ultimate consequence of stellar evolution for the universe's most massive stars. On the other hand, if the star sheds enough mass during its violent life and in the supernova itself, the remnant core might form a neutron star instead. Neutron stars are equally extraordinary in their own right. Ultra-dense objects where a single teaspoon of matter would weigh billions of tons on Earth. The collapse of the core compresses protons and electrons together to form neutrons, creating a compact, city-sized sphere with a magnetic field billions of times stronger than that of the Sun. A neutron star left behind by Westerlund 1-26 would likely spin rapidly, emitting beams of radiation that could sweep across space as a pulsar. Though smaller than black holes, neutron stars are no less extreme. They represent the violent, compressed remnants of a massive star's core, showcasing the immense densities and pressures achievable in the universe. The supernova event that ushers in either of these outcomes is itself one of the most energetic phenomena in the cosmos. When Westerlund 1-26 finally collapses, the outer layers will be expelled at a significant fraction of the speed of light, releasing energy that can briefly outshine entire galaxies. The shockwave from such an explosion would tear through the surrounding interstellar medium, compressing gas clouds and potentially triggering new waves of star formation. Simultaneously, the explosion would scatter the heavy elements produced over the star's lifetime into space, contributing to the cosmic cycle of creation. Iron, carbon, oxygen, and other metals forged in the heart of Westerlund 1-26 will seed future stars, planets, and even life itself, highlighting the paradoxical nature of these cataclysmic events. They are both destructive and generative. The specifics of the collapse are influenced by the tremendous instability Westerlund 1-26 exhibits now. Its violent stellar winds and episodic mass ejections in recent millennia may have reduced the core's mass just enough to tip the balance between forming a black hole or a neutron star. Observations of its pulsations and the distribution of its outer material suggest that the final collapse could be preceded by additional mass loss events or smaller eruptions, each slightly altering the structure of the core and the mechanics of the imminent supernova. In this sense, Westerlund 1-26 is a star in which the final act is being choreographed in real time, a drama of physics playing out across thousands of years that we glimpse only in snapshots of data captured by telescopes. Regardless of whether the remnant is a black hole or a neutron star, the collapse of Westerlund 1-26 will be transformative for its surroundings. Nearby stars, gas clouds, and dust will feel the effects of the released energy, and the cluster that cradled this stellar giant will be reshaped by the explosion. The remnant core, whether hidden within an event horizon or compacted into a neutron star, will continue to influence its environment gravitationally, guiding the motion of nearby objects and subtly shaping the evolution of its region of the galaxy. In the larger cosmic context, Westerlund 1-26's collapse is a single moment in the ongoing story of matter, energy, and the life cycles of stars. Yet it stands out because of the sheer scale and power involved. Ultimately, the imminent collapse of Westerlund 1-26 is a reminder of the transient nature of even the universe's most massive and imposing structures. A star that once dwarfed millions of suns will be reduced to either a black hole or a neutron star, a fraction of its former size, yet infinitely dense and powerful in new ways. The energy, light, and material expelled during this final act will ripple across space, leaving both a legacy and a warning. It is a vivid demonstration that the universe is not static or gentle. It is a realm of extremes, where even the mightiest stars are fated to die in spectacular violence, and where the processes of destruction and creation are inseparably intertwined. Westerlund 1-26, in its final moments, embodies this cosmic truth with a scale and intensity that few objects in the universe can rival. The supernova of Westerlund 1-26 promises to be one of the most violent and awe-inspiring events in the universe, a cosmic detonation so extreme that it dwarfs nearly all familiar astronomical phenomena. When the star finally reaches the end of its life, the fusion processes in its core will cease abruptly, leaving nothing to counterbalance the enormous gravitational forces pressing inward. In an instant, the core will collapse, and the outer layers, already unstable and tenuously bound, will be violently expelled into space. The energy released during this cataclysm will be almost incomprehensible. Estimates suggest that the total energy output could exceed that produced by the Sun over its entire 10 billion year lifetime. For a brief period, the supernova could shine with the brightness of an entire galaxy, momentarily illuminating the darkness of space across tens of thousands of light years. It is not merely an explosion. It is a concentrated release of power at a scale that challenges the very limits of imagination. This supernova, classified as a Type II event due to the collapse of a massive stellar core, will unfold in a dramatic sequence. The shockwave generated by the imploding core will rebound outward, slamming into the star's outer envelope and accelerating it to enormous velocities, potentially tens of thousands of kilometers per second. As the material races away, it will collide with previously ejected stellar winds, generating brilliant flashes of radiation and producing complex, turbulent structures in the expanding supernova remnant. Observers within thousands of light years could, hypothetically, witness a sudden increase in brightness as the formerly dim red supergiant becomes a dazzling beacon across the cosmos. This explosion is a violent release of not just light, but kinetic energy, heat, and electromagnetic radiation in forms that can influence surrounding stars and interstellar clouds. The scale of the energy involved is staggering when considered in absolute terms. While the Sun emits roughly 3.8 times 10 to the 26th watts per second, the energy unleashed by Westerlund 1-26's supernova in just a few seconds or minutes will dwarf that by a factor of billions or even trillions. It is an event capable of reshaping the local stellar neighborhood, compressing gas clouds, and potentially triggering the formation of new stars. The material expelled in the explosion is rich with heavy elements: carbon, oxygen, silicon, iron, and beyond, synthesized over the star's lifetime through successive stages of nuclear fusion. These elements are essential for the formation of rocky planets, moons, and the basic building blocks of life, meaning that even in its death, Westerlund 1-26 contributes to the creation of the next generation of stars and planetary systems. The supernova will also produce intense radiation, including X-rays and gamma rays, as well as a flood of neutrinos from the core collapse. These particles will surge outward at nearly the speed of light, carrying information about the extreme processes within the dying star. For astronomers, such a supernova represents a rare opportunity to study the physics of massive stars at the moment of their destruction. Models of stellar collapse, nucleosynthesis, and shockwave propagation can be tested and refined based on observations of these rare events. Each supernova, especially one as powerful as Westerlund 1-26's, is effectively a laboratory for the universe, allowing scientists to understand not only the life cycles of stars, but also the processes that shape galaxies. The consequences of such a supernova, if it were closer to Earth, are almost unimaginable. While Westerlund 1-26 lies safely thousands of light years away, hypothetically placing it within a few hundred light years would expose the planet to lethal levels of radiation, potentially stripping the atmosphere and causing mass extinction. Even at its actual distance, the energy released is so immense that it alters the dynamics of the surrounding cluster and contributes significantly to the evolution of the interstellar medium. The shockwaves compress nearby molecular clouds, potentially triggering new waves of star formation, while the expelled heavy elements seed the environment with the materials needed to form planets, moons, and life itself. In this sense, the supernova is both an agent of destruction and a catalyst for creation, a paradoxical event that epitomizes the dual nature of the universe's most massive stars. In addition to the visible brilliance, the kinetic energy of the ejected matter from Westerlund 1-26 will be extraordinary. The expanding shells of gas and dust, moving at a significant fraction of the speed of light, will interact with the surrounding interstellar medium, creating shock fronts and accelerating particles to near relativistic speeds. These interactions can produce cosmic rays and high-energy radiation that propagate across vast distances, influencing the chemistry and dynamics of far-off regions in the galaxy. The supernova remnant, long after the initial explosion fades, will remain a vibrant, turbulent structure, a testament to the immense forces released during the star's final moments. It is a vivid example of how even the death of a single star can ripple across the cosmos, altering environments and setting the stage for future stellar generations. Ultimately, the supernova of Westerlund 1-26 embodies the terrifying power of nature at its most extreme. It is the culmination of millions of years of furious fusion, instability, and mass loss, a release of energy so vast that it can outshine entire galaxies and reshape the material of its surroundings. The star's eventual explosion will not only signal the end of a cosmic titan, but also act as a transformative force in the galaxy, scattering elements, triggering new stars, and imprinting its legacy across the interstellar medium. In witnessing or even imagining such an event, humans confront the sheer scale and intensity of the universe, a reminder that celestial phenomena operate on levels far beyond everyday comprehension, where creation and destruction are inseparably intertwined, and where the life of a single star can have repercussions across light years of space. Beyond the already unimaginable energy of a supernova, Westerlund 1-26 harbors the potential for an even more terrifying cosmic event: the formation of a gamma-ray burst. These bursts are among the most powerful and energetic phenomena in the known universe, capable of releasing in seconds more energy than our Sun will emit over its entire 10 billion-year lifetime. While a typical supernova distributes energy spherically in all directions, a gamma-ray burst focuses an enormous amount of energy into a narrow beam. If such a burst were aligned toward Earth, even at thousands of light-years away, the consequences would be catastrophic. Intense gamma radiation could strip away the atmosphere, obliterate the ozone layer, and trigger mass extinction events on a planetary scale. The idea that Westerlund 1-26 could produce a gamma-ray burst makes it not only a spectacular cosmic object, but also a terrifying reminder of the universe's raw, destructive power. Gamma-ray bursts are usually associated with the collapse of extremely massive stars, particularly those that are rapidly rotating. Westerlund 1-26, with its immense mass and turbulent evolutionary stage, fits the profile of a star capable of producing such an event under the right conditions. As the star's core collapses, conservation of angular momentum could cause it to spin at incredible rates, forming a dense, rotating core. If this core collapses into a black hole, surrounding material can form an accretion disk, funneling energy along the rotational axis and producing jets of gamma radiation that shoot into space at nearly the speed of light. These relativistic jets are the defining feature of a gamma-ray burst, concentrating energy that would otherwise be spread over an entire sphere into narrow, laser-like beams, capable of crossing tens of thousands of light-years. The formation of a gamma-ray burst from Westerlund 1-26 would not be a slow, drawn-out process. It could happen in seconds or minutes, an almost instantaneous release of energy on a scale that dwarfs any human comprehension. During this fleeting moment, the energy radiated in gamma rays would be so intense that it could alter the chemistry of the interstellar medium it passes through. High-energy photons from the burst can ionize atoms, break molecular bonds, and accelerate charged particles to near-relativistic speeds. These effects propagate far beyond the immediate vicinity of the star, influencing not just the star cluster Westerlund 1 resides in, but potentially regions of the galaxy hundreds or thousands of light-years away. The reach and intensity of a gamma-ray burst highlight the profound interconnectedness of cosmic events, demonstrating that a single star's death can have consequences across unimaginable distances. Even the prospect of a gamma-ray burst underscores the precarious balance inherent in the life cycle of massive stars. Westerlund 1-26 has already shed massive amounts of material through stellar winds and pulsations, and this shedding might influence whether a gamma-ray burst occurs. If enough angular momentum is retained in the collapsing core, the conditions are ripe for a burst. If not, the collapse may produce a supernova without the focused gamma emission. Scientists studying such stars must consider rotation rates, magnetic fields, and internal mass distribution to model the likelihood of these bursts. Every observation, from fluctuations in luminosity to irregularities in expelled matter, contributes to our understanding of whether Westerlund 1-26 could unleash this extraordinary event. The consequences of a gamma-ray burst are even more dramatic when considering its potential effects on planets and life. Unlike the broader light of a supernova, which dissipates over vast distances, the focused energy of a gamma-ray burst can concentrate enough power to sterilize planets directly in its path. It can deplete atmospheric ozone, exposing surfaces to lethal ultraviolet radiation from nearby stars, or even trigger chemical reactions that permanently alter planetary atmospheres. In the history of Earth and other planets, gamma-ray bursts have been hypothesized as potential triggers for mass extinction events, though fortunately none have occurred close enough to Earth to have caused global devastation. Westerlund 1-26, as a candidate for such an event, serves as both a cosmic spectacle and a chilling warning of the destructive potential lurking in distant star clusters. The possibility of a gamma-ray burst also emphasizes the dual nature of massive stars as both creators and destroyers. While Westerlund 1-26 enriches its surrounding galaxy with heavy elements and fuels star formation through its supernova, the potential burst of focused energy represents the ultimate expression of destructive power in the cosmos. It is a stark reminder that the same processes that enable creation, collapse, fusion, and rotation can, under extreme conditions, unleash forces capable of obliterating entire planetary systems. For astronomers and astrophysicists, studying stars like Westerlund 1-26 is not merely a matter of curiosity. It is an exploration of the fundamental physics that govern both life and death on cosmic scales. Ultimately, the gamma-ray burst threat associated with Westerlund 1-26 magnifies the awe-inspiring, terrifying power of the universe. Here exists a star so massive, so unstable, and so energetic that its death could produce a beam of radiation crossing thousands of light years, altering planets, stars, and interstellar clouds in its path. It is a reminder that the cosmos is not only beautiful but unpredictable, where creation and destruction are intertwined, and where objects of unimaginable scale can produce events that dwarf human comprehension. Westerlund 1-26, in this sense, is both a marvel and a warning. A stellar titan whose life and potential death reveal the raw, unrelenting energy of the universe. If Westerlund 1-26 were located just a few hundred light years from Earth, the very idea of its existence becomes terrifying. At its current distance of 14,000 to 16,000 light years, we are fortunate that its eventual supernova and any potential gamma-ray burst pose no direct threat to life on our planet. But proximity changes everything. A star of this magnitude, with its unparalleled size, mass, and energy output, exploding even a fraction of the distance closer, would unleash catastrophic consequences for the entire solar system. The light from the supernova alone would rival the sun in brightness, overwhelming the night sky, and for days or even weeks, Earth would experience radiation levels far beyond what its atmosphere could normally absorb. The heat, X-rays, and gamma rays would bombard the planet relentlessly, fundamentally altering its atmosphere, oceans, and surface conditions in ways that would likely render it uninhabitable. The effects of such a nearby supernova would begin with the obliteration of the ozone layer. Gamma rays and high-energy X-rays from the explosion would penetrate the atmosphere, breaking apart molecular bonds and triggering chemical reactions that deplete ozone. Without this protective shield, the sun's ultraviolet radiation would strike the surface unfiltered, causing widespread environmental damage and mass extinctions. The intensity of the radiation from Westerlund 1-26's supernova would be unlike any solar storm or ordinary cosmic event. It would overwhelm natural planetary defenses. On top of that, the influx of charged particles and cosmic rays would create further devastation, stripping away portions of the atmosphere, damaging the biosphere, and potentially triggering long-term climate effects that could last centuries. The sheer energy involved in the supernova also presents a kinetic threat. The shockwave produced by the explosion, carrying enormous amounts of matter expelled at relativistic speeds, would collide with the interstellar medium surrounding the solar system. At only a few hundred light-years away, this shockwave could compress the heliosphere, the protective bubble created by the sun's solar wind, allowing high-energy cosmic particles to penetrate even further into the inner solar system. Planets like Earth, Mars, and Venus would be exposed to radiation and particle fluxes far beyond anything seen in recorded history. Satellites, electrical grids, and communication systems, if humanity survived the initial blast, would be decimated. The potential for ecological collapse would be enormous, making the solar system a barren zone of cosmic fallout. Even the visual and thermal impact would be staggering. A nearby Westerlund 1-26 supernova would outshine the sun in our sky, turning night into day and temporarily altering temperatures on Earth. Plants and animals would experience sudden changes in light and radiation exposure, disrupting ecosystems that have evolved under stable cycles of sunlight. The supernova's light would not just be bright, it would be suffocatingly intense, penetrating into oceans and land masses, altering biological processes in ways that could ripple across the food chain. The entire biosphere would be subjected to stress at a scale no terrestrial event could replicate, demonstrating the destructive potential of a star that dwarfs even our Sun by millions of times in energy output. Adding to this is the long-term threat of a gamma-ray burst, should Westerlund 1-26's collapse produce one aligned with Earth. A focused gamma-ray beam aimed directly at the planet would deliver lethal doses of radiation in a matter of seconds, sterilizing the surface almost instantaneously. Unlike the supernova, which disperses energy relatively evenly, the concentrated energy of a gamma-ray burst could remove the ozone layer almost entirely, boil away surface water, and irradiate everything living. The damage would extend beyond the immediate atmosphere, potentially causing permanent changes to climate, chemistry, and planetary habitability. The very notion of such a burst makes the star's proximity an existential threat. Even advanced civilizations with protective technologies would find it nearly impossible to survive intact. From a cosmic perspective, proximity also intensifies the gravitational and environmental influences of the star. While 14,000 light-years is a safe distance, at only a few hundred light-years, the gravitational pull of a star of Westerlund 1-26's mass could have subtle effects on the orbits of nearby stars, planetary bodies, and interstellar clouds. The expelled mass from stellar winds and the supernova itself would sweep through the local interstellar medium with far greater intensity, potentially compressing gas clouds in ways that trigger uncontrolled star formation or alter the trajectories of neighboring systems. Essentially, the star would become a local agent of chaos, reshaping its surroundings violently and unpredictably, far beyond the mere spectacle of its supernova. Even human observation would be impossible to endure. The combination of blinding light, extreme radiation, and charged particle bombardment would make direct observation deadly. Telescopes and satellites would be destroyed, instruments would fail, and survival above the surface of Earth would be virtually impossible. Any attempt to shield from the explosion would require technologies far beyond anything humanity currently possesses. From this perspective, the thought experiment of Westerlund 1-26 being nearby emphasizes not just the star's scale and energy, but also the fragility of planets like Earth in the face of extreme cosmic events. Ultimately, imagining Westerlund 1-26 within a few hundred light-years transforms it from a distant wonder into a planet-destroying titan. Its supernova would not merely be spectacular, it would be an extinction-level event, capable of erasing the surface biosphere and altering the solar system's environment irreversibly. The immense energy radiated in light, heat, X-rays, gamma rays, and kinetic material would strike like a cosmic hammer, reminding us that proximity is everything when it comes to the universe's most extreme phenomena. Thankfully, this star remains thousands of light years away, giving humanity and Earth the benefit of safety while allowing us to marvel at its incredible size, power, and eventual fate from afar. Westerlund 1-26 is not merely a spectacle of size and power, it is also a cosmic alchemist, transforming the simplest elements into the building blocks of the universe and scattering them across the galaxy in one of the grandest processes of stellar evolution. Massive stars like this red supergiant play a crucial role in the chemical enrichment of galaxies. During their lifetimes, they fuse lighter elements like hydrogen and helium into progressively heavier elements through nuclear fusion in their cores. This process, occurring over millions of years, produces carbon, oxygen, nitrogen, silicon, and eventually iron, the very materials that make up planets, moons, and life itself. In essence, stars like Westerlund 1-26 are factories of matter, continuously forging the components that allow the universe to grow more complex. When the inevitable supernova occurs, this transformation reaches its climax. The explosion violently expels the star's outer layers, enriched with these heavy elements, into the surrounding interstellar medium. Unlike smaller stars, which may quietly fade into white dwarfs, the death of a massive star is a cosmic fireworks display, distributing its accumulated riches across thousands of light years. The ejected material mixes with surrounding gas and dust, creating a chemically diverse environment ripe for new star formation. This enrichment process is essential to galactic evolution. Without supernovae like that of Westerlund 1-26, subsequent generations of stars would be born from mostly pristine hydrogen and helium, limiting the development of planets and, ultimately, the possibility of life. Beyond enriching the interstellar medium, the expelled matter from massive stars also shapes the physical structure of galaxies. The shockwaves generated by supernovae compress surrounding gas clouds, triggering the collapse of these clouds into new stars. This creates waves of star formation, particularly in starburst regions, and contributes to the dynamic and ever-changing architecture of galaxies. Westerlund 1-26's supernova will send ripples through its cluster, shaping not only the chemical composition, but also the density, temperature, and distribution of nearby molecular clouds. The star's death will effectively sculpt its galactic neighborhood, demonstrating that the life cycle of massive stars is a primary driver of both chemical and structural evolution in galaxies. The heavy elements released are especially critical because they enable the formation of complex chemistry in future planetary systems. Elements like carbon, oxygen, nitrogen, magnesium, and iron, forged in Westerlund 1-26's core, are the foundational ingredients for rocky planets, water, and organic molecules. Every atom heavier than helium in our bodies was once synthesized in the cores of stars and dispersed through events like supernovae. Westerlund 1-26, in its final moments, will contribute to this cosmic legacy, seeding the galaxy with the materials necessary for life to arise. In this way, the star is not only a destroyer, but also a creator, its violent death directly enabling the conditions for new worlds and, potentially, new life forms elsewhere in the cosmos. The impact of a single massive star on its galaxy may seem almost inconceivable, yet stars like Westerlund 1-26 dominate the evolution of star clusters and, by extension, the broader galactic environment. Their immense luminosity and energetic winds stir the surrounding interstellar medium, while their ultimate explosions distribute newly forged elements far and wide. Over cosmic time, these processes accumulate, gradually transforming galaxies from clouds of primordial hydrogen and helium into rich, chemically diverse systems. The supernovae of massive stars are thus not isolated events. They are fundamental acts in the ongoing creation and evolution of galaxies, linking the life and death of individual stars to the broader cosmic ecosystem. Furthermore, the legacy of Westerlund 1-26 is not limited to elements alone. The energy it releases during its final supernova will propagate through space, creating high-energy particles and shockwaves that can influence the formation of other stars, compress interstellar gas, and even affect the trajectories of nearby stellar objects. These processes illustrate the interconnectedness of cosmic events. The life of a single star can shape the evolution of its entire neighborhood, and the death of a supergiant can trigger the birth of new stars. It is a cycle of destruction and creation on scales that dwarf human comprehension, demonstrating that massive stars are both architects and agents of change within their galaxies. In this sense, Westerlund 1-26 exemplifies how stars of extreme mass act as the universe's primary engines of transformation. From the moment they ignite, they alter their surroundings through radiation, stellar winds, and gravity. At the end of their lives, they enrich and energize the cosmos through explosive deaths. Each supernova contributes to the formation of planets, the chemical complexity necessary for life, and the ongoing evolution of galaxies. The enormous scale of Westerlund 1-26 means that its contribution will be extraordinary, leaving a mark on the galaxy that persists long after the star itself has vanished. Its life and death illustrate the paradoxical nature of massive stars, simultaneously destructive and generative, fleeting in time, yet enduring in influence. Ultimately, the story of Westerlund 1-26 as a star that shapes galaxies underscores the intricate interplay between matter, energy, and evolution in the universe. While the star's immense size, catastrophic death, and potential gamma-ray bursts inspire awe and fear, its role as a cosmic architect is equally remarkable. Through its fusion of elements, stellar winds, and final supernova explosion, it participates in the ongoing creation of the cosmos, scattering the seeds of future worlds and life across space. Westerlund 1-26 is a testament to the profound power of massive stars, a reminder that the universe's most awe-inspiring objects are not merely passive wonders to observe, they are active participants in the ongoing story of cosmic evolution. Westerlund 1-26 does not exist in isolation. It resides in the heart of the Westerlund 1-star cluster, one of the most extreme and remarkable star-forming regions in the Milky Way. This cluster is a densely packed collection of massive stars, containing dozens of supergiants, hypergiants, and other stellar behemoths, all within a relatively compact region of space. The sheer number of enormous stars coexisting in such proximity makes Westerlund 1 a laboratory for understanding the physics of stellar evolution at the upper extremes of mass. Each of these massive stars is contributing to a dynamic, turbulent environment with intense radiation, violent stellar winds, and complex gravitational interactions sculpting the interstellar medium in real time. The cluster itself is roughly 14,000 to 16,000 light-years from Earth, hidden within the constellation of Ara, yet its density and the scale of its stars make it extraordinary. Westerlund 1-26 stands out even among these giants, but it shares its environment with other massive stars that are also approaching the ends of their lives. Many of these stars are blue supergiants, yellow hypergiants, and other red supergiants, forming a collective furnace that illuminates the cluster while also ejecting tremendous amounts of mass into the surrounding space. The interplay of radiation and stellar winds from dozens of such massive stars creates a chaotic, high-energy environment in which gas clouds are compressed, heated, and sometimes triggered to form new stars. The cluster, in effect, is a stellar nursery and a graveyard simultaneously, a place where stars are born in turbulent conditions and die with explosive consequences. The high concentration of massive stars in Westerlund one has significant implications for the dynamics and evolution of the cluster. The combined gravitational pull of these enormous bodies influences the orbits and stability of stars within the cluster, sometimes resulting in close encounters, stellar collisions, or mass transfers between binary systems. These interactions can accelerate the evolution of individual stars, hastening their progress towards supernova or altering their life cycles in unpredictable ways. In particular, Westerlund 1-26's own evolution may have been influenced by neighboring stars, as their combined radiation pressure and gravitational forces help shape the outer layers and stellar winds of each cluster member. This creates a tightly coupled system where the life of one massive star is intricately linked to the others around it. The cluster is also remarkable for the variety of extreme stellar types it contains. Beyond red supergiants like Westerlund 1-26, there are numerous luminous blue variables and Wolf-Rayet stars, each representing different pathways of stellar evolution, but all sharing immense mass and luminosity. Wolf-Rayet stars, in particular, are shedding mass at phenomenal rates, contributing enriched material to the cluster and highlighting the life cycle stages that Westerlund 1-26 will eventually traverse. The presence of so many massive stars in a single cluster makes Westerlund 1 not just a collection of stars, but a microcosm of stellar evolution, offering astronomers a chance to study multiple evolutionary outcomes in one environment and observe how extreme stellar physics operates in real time. The sheer energetic output of the cluster is staggering. The combined radiation from all these massive stars floods the surrounding gas and dust with ionizing photons, carving out cavities in the molecular clouds from which they formed. These cavities, sculpted by stellar winds and radiation, can influence the formation of subsequent generations of stars, dictating where dense gas can collapse and where it will be dispersed. Essentially, the cluster acts as a dynamic ecosystem, with each massive star influencing the birth, life, and death of its neighbors. Westerlund 1-26, as the largest and one of the most luminous members, dominates this ecosystem, but it is supported and shaped by the collective presence of its stellar peers. The proximity of so many massive stars also amplifies the cluster's potential for spectacular cosmic events. With multiple red supergiants and hypergiants nearing the ends of their lives, Westerlund 1 is effectively a ticking time bomb of supernovae. When these stars begin to collapse, their explosions will not occur in isolation, but in a densely packed stellar environment, potentially interacting with the stellar winds, magnetic fields, and remnants of other massive stars. Such clustered supernovae could influence the chemical evolution of the cluster more dramatically than isolated explosions would, enriching the surrounding interstellar medium with heavier elements at an accelerated rate and creating shock waves that propagate in complex overlapping patterns. The cluster is a stage where both creation and destruction occur simultaneously, amplified by the sheer number and proximity of its stellar giants. In terms of observation and scientific significance, Westerlund 1 is a treasure trove. By studying the cluster, astronomers can examine the extremes of stellar mass, the effects of dense stellar environments, and the physics of high-energy radiation and mass loss in massive stars. Each member provides a case study in how stars evolve, interact, and ultimately die, with Westerlund 1-26 serving as the ultimate example of what a massive star can become. The cluster demonstrates that the universe is capable of producing environments so dense, energetic, and extreme that they defy ordinary understanding of stellar behavior, offering a glimpse into processes that are both violent and awe-inspiring. Ultimately, the presence of Westerlund 1-26 within such an extraordinary cluster highlights the interdependence of massive stars and their environments. The star is a product of its cluster's unique conditions and, in turn, a dominant force shaping that environment. The collective radiation, winds, and eventual supernovae of Westerlund 1's members are a testament to the dynamic, interconnected nature of stellar nurseries, where extreme stars live short, intense lives that leave lasting imprints on their surroundings. Westerlund 1-26, towering above its neighbours in size and power, exemplifies how the life and death of massive stars are not solitary events. They are the orchestrated movements of cosmic giants within a vibrant and perilous stellar ecosystem. To truly grasp the magnitude of Westerlund 1-26, it helps to visualize it not in isolation, but in terms that relate to our own solar system. Its size, already staggering when compared to other known stars, becomes almost incomprehensible when imagined in place of our Sun. The radius of Westerlund 1-26 is estimated to be over 1,500 times that of the Sun, which would extend far beyond the orbit of Jupiter if placed at the center of our solar system. Mercury, Venus, Earth, Mars, and even the asteroid belt would all lie within the fiery envelope of this colossal star. The sheer scale is so vast that our intuitive understanding of distance, space, and size begins to break down. The Earth itself would be nothing more than a tiny speck engulfed in the star's outer layers, completely swallowed by its incandescent mass. Even the planets further out would be dwarfed in comparison. Saturn, Uranus, and Neptune would exist at the edge of or beyond the star's outer layers, but they too would be at risk from the extreme temperatures and radiation permeating the star's vast atmosphere. The entire inner solar system, the cradle of life as we know it, would be obliterated by the sheer size and heat of Westerlund 1-26. To imagine this is to confront a scale of magnitude that strains human comprehension. A single star capable of containing planets, asteroids, and more, entirely consuming a region of space that we consider vast in ordinary terms. If we could shrink the Sun to the size of a basketball, Westerlund 1-26 would be comparable to a sphere over 25 meters across. A mind-bending comparison that makes the vastness of the cosmos feel simultaneously intimate and terrifying. The mass of Westerlund 1-26 also contributes to this sense of incomprehensible scale. While radius gives a sense of size, its mass, several tens of times that of the Sun, amplifies the gravitational power it exerts. This gravity is not merely a force, it is a cosmic architect capable of influencing the structure and movement of nearby stars and gas clouds. In our hypothetical solar system, this immense gravitational pull would completely destabilize planetary orbits long before the star physically engulfed them. Earth, Jupiter, and even Saturn would be subjected to tidal forces so intense that they could be torn apart or pulverized by the gravitational stress. The combination of scale, heat, and gravitational influence paints a picture of a celestial object so extreme that the very concept of a solar system as we know it becomes meaningless in its presence. Beyond our solar system, the implications of such a star's energy output are equally staggering. Westerlund 1-26 radiates more energy in a single second than the Sun produces in an entire year. If it were positioned within even a few hundred light-years of Earth, the intensity of this radiation would be lethal, capable of stripping the atmosphere, boiling oceans, and eradicating virtually all life. The heat and light from the star would be so overwhelming that planetary surfaces could not exist in anything resembling stable conditions. This is not science fiction. This is a real, tangible measure of the destructive power inherent in the most massive stars. To place it at the center of our solar system is to confront an object whose scale defies ordinary comprehension, where planets are reduced to mere specks in a sea of incandescent plasma. To further illustrate, consider the volume of Westerlund 1-26. Its radius is over 1,500 times that of the Sun, which means its volume is not merely 1,500 times greater, but astronomically more, because volume scales with the cube of the radius. Rough calculations suggest that it could contain over 3.4 billion suns within its outer layers. To visualize this is nearly impossible. Every star we can see in the night sky, every energy source we know, is dwarfed inside a single celestial body. The density, while lower than the Sun, due to its extended outer layers, does not diminish the sense of scale. We are speaking of a single star capable of holding billions of solar masses worth of material in its volume, a true titan of the cosmos. The star's outer layers, composed of superheated plasma, extend so far that they blend into the surrounding interstellar medium, creating an envelope that is both physically enormous and energetically intense. Westerlund 1-26's surface temperature is cooler than smaller stars like our Sun, but this is relative, even at a few thousand degrees Kelvin. The energy radiated across such an enormous surface is overwhelming. The combination of size and energy output ensures that the star dominates its local environment, heating surrounding gas clouds, influencing the formation of nearby stars, and injecting vast quantities of heavy elements into space. Its mere presence reshapes the stellar neighborhood, affecting everything within tens of light years, and hypothetically, within the solar system, it would obliterate the delicate balance that allows planets to exist. The star's instability adds yet another layer to this mind-bending scale. Westerlund 1-26 is shedding mass at phenomenal rates through intense stellar winds, losing material equivalent to multiple suns over relatively short astronomical timescales. This constant shedding further expands the star's envelope, creating regions of extremely hot plasma that extend far beyond the already enormous physical radius. Were this star to occupy the Sun's position, its stellar winds alone would interact catastrophically with Earth's atmosphere and magnetic field, stripping away protective layers and exposing the surface to lethal levels of radiation even before the star's eventual supernova. The combination of sheer size, energy output, and violent mass loss means that imagining Westerlund 1-26 in our solar system is to imagine a complete annihilation of familiar celestial architecture. Comparisons to other massive stars like UY Scuti and VY Canis Majoris further emphasize the uniqueness of Westerlund 1-26. While UY Scuti may be better known for its enormous size, Westerlund 1-26 surpasses it in sheer radius and mass, emphasizing that the universe can create stars so extreme that even among giants, it stands out. The energy released from its surface, the scale of its volume, and the rapidity of its evolution collectively place it in a class apart, a cosmic titan that dwarfs even the most legendary stellar behemoths. This comparison underscores not just the magnitude of the star itself, but also the rarity and extremity of objects that reach such scales in the universe. In conceptual terms, the Earth would be swallowed not only physically, but energetically. Its atmosphere, oceans, and magnetic field would be overwhelmed by the star's heat and radiation. The notion of survival becomes meaningless. The planet would be enveloped in incandescent plasma, and even the core would be subjected to unimaginable forces. From a cosmic perspective, Westerlund 1-26 serves as a humbling illustration of the disparity between human experience and the extreme conditions that exist in the universe. A single object can dwarf planets, entire solar systems, and billions of suns in volume, reminding us of our own smallness and fragility in the face of cosmic phenomena. Furthermore, thinking about the scale of time amplifies this awe. While the Sun will burn steadily for around 10 billion years, Westerlund 1-26's immense size and rapid fuel consumption mean that it will exist in this extraordinary state for only a few million years. A fleeting moment in cosmic terms. During this brief existence, it radiates power, sheds mass, and dominates its environment to a degree that smaller stars cannot match. Its life cycle, though brief, is extreme in every measurable way, reinforcing that size and energy in the universe are often correlated with brevity, intensity, and instability. The star is a fleeting monument to the raw power of stellar evolution, an object that exemplifies the paradox of cosmic grandeur, immense, violent, and ephemeral all at once. The mind-bending nature of Westerlund 1-26 also becomes apparent when considering its eventual death. When this star reaches the end of its life, the resulting supernova will unleash energy that could outshine entire galaxies, distributing billions of solar masses worth of elements into space. Were this star at the center of our solar system, that cataclysmic explosion would obliterate all planets within its radius and sterilize or destroy even more distant bodies with gamma radiation and stellar ejecta. The scale of destruction is as vast as the star itself, illustrating that magnitude is not confined to size, but extends into energy, influence, and the potential for cosmic transformation. Ultimately, imagining Westerlund 1-26 replacing the Sun forces us to confront the limits of comprehension. The Earth, the planets, and the entire inner solar system would be swallowed inside it, our familiar cosmic neighborhood utterly subsumed by plasma, gravity, and energy on scales that stretch beyond human imagination. It is a star so large, so violent, and so extreme that ordinary comparisons fail to convey the sheer enormity of its presence. By placing it in the context of the solar system, we begin to understand not just the quantitative size of Westerlund 1-26, but the qualitative leap in scale, energy, and influence that it represents. A cosmic titan whose magnitude humbles the imagination and reminds us of the vastness and power inherent in the universe. Westerlund 1-26, despite its enormous size and power, exists in a state of extreme temporal fragility. Its immense mass, which allows it to dominate the cosmos with light, heat, and gravitational influence, comes with a cosmic price, a lifespan that is almost incomprehensibly short when measured against more modest stars like our Sun. While the Sun will persist for approximately 10 billion years, fusing hydrogen into helium in a slow, steady process that allows for the formation of planets, life, and a stable solar system. A supergiant like Westerlund 1-26 lives fast and dies young. Its total lifespan is measured in only a few million years, a blink of an eye on a cosmic timescale, and a stark illustration of the trade-off between size, luminosity, and longevity. The physics behind this accelerated life cycle is both fascinating and brutal. Stars generate energy through nuclear fusion, converting hydrogen into helium and, at later stages, fusing heavier elements in their cores. In massive stars like Westerlund 1-26, the core pressures and temperatures are enormous due to the star's gravity and mass. These extreme conditions accelerate fusion reactions to rates far beyond what occurs in a smaller star like the Sun. While the Sun burns its hydrogen fuel at a leisurely pace, a star like Westerlund 1-26 consumes its supply with catastrophic rapidity. This means that, despite containing far more hydrogen than the Sun, it exhausts this fuel in mere millions of years rather than billions. Its very size ensures that it burns hotter, brighter, and faster, a literal cosmic embodiment of intensity and impermanence. As Westerlund 1-26 progresses through its short life, it passes through evolutionary stages at a pace that dwarfs human comprehension. Early in its life, it likely existed as a blue supergiant, shining with tremendous energy and influencing its surroundings with radiation and stellar winds. As hydrogen in the core was depleted, the star expanded into a red supergiant, swelling to a radius over 1,500 times that of the Sun. These transitions happen on timescales of hundreds of thousands to millions of years, fast by astronomical standards, and demonstrate that every phase of a supergiant's existence is both intense and transient. While the Sun's slow, steady evolution allows for billions of years of relative stability, Westerlund 1-26 has only a fleeting period in which it dominates its environment, and every second brings it closer to the inevitability of collapse and supernova. The brevity of life in massive stars has dramatic consequences for their surroundings. Because Westerlund 1-26 lives so fast, it injects enormous quantities of energy, radiation, and stellar wind into the surrounding space within a very short period. The cluster in which it resides, Westerlund 1, experiences extreme levels of ionizing radiation, shockwaves from mass ejection, and rapid enrichment with heavy elements, all on a timescale of a few million years. In comparison, stars like the Sun produce gentler radiation and evolve slowly, giving planets and life the time to adapt and ecosystems the opportunity to develop. A supergiant, by contrast, is both a creator and destroyer within a brief cosmic heartbeat, leaving profound impacts on its stellar neighborhood despite its fleeting existence. The short lifespan also underscores the inevitability of Westerlund 1-26's death. The forces that drive it to radiate so prodigiously are the same forces that ensure it cannot endure. Once the star has exhausted its nuclear fuel, the balance between internal pressure and gravity collapses, leading to catastrophic core implosion and a violent supernova explosion. In the brief timeline of a few million years, the star moves from formation to total destruction, completing a life cycle that dwarfs human history, yet is minuscule in the cosmic calendar. Unlike smaller stars that fade gradually, supergiants reach the climax of their evolution quickly, and the universe witnesses the extremes of creation and annihilation within a fleeting span. This temporal extremity also provides insights into stellar populations and galactic evolution. Because massive stars live such short lives, they are rarely observed outside active star-forming regions like Westerlund 1. Their scarcity in older stellar populations reflects the brevity of their existence and emphasizes that what we see today is a snapshot of a dynamic and rapidly changing stellar environment. Every supergiant observed is, in essence, in a last act before the ultimate explosion, a fleeting window into processes that shape galaxies, create heavy elements, and drive cosmic evolution on enormous scales. Westerlund 1-26 is therefore not only awe-inspiring for its size, but also for the urgency inherent in its existence. Every second matters, and every moment is a step closer to its dramatic end. The combination of size, energy, and brevity makes Westerlund 1-26 a stark contrast to smaller, more stable stars. While the Sun provides billions of years of steady energy to sustain life, supergiants are engines of extreme physics, burning furiously and releasing prodigious energy in a few million years before ceasing to exist entirely. This contrast highlights the delicate balance required for stability and life in the universe, and the role that massive stars play as both agents of destruction and facilitators of future cosmic formation. The clock of a supergiant ticks with relentless speed, a reminder that the universe operates on scales of intensity and impermanence far beyond human experience. Moreover, the short lifespan of stars like Westerlund 1-26 amplifies the sense of inevitability surrounding its future. While humans often perceive stars as eternal, massive stars exist under an entirely different temporal regime, one where growth, peak luminosity, and collapse are compressed into a cosmic sprint. The star's rapid evolution from formation to death means that we are witnessing an extraordinary moment in time, a rare glimpse of a supergiant in its advanced stage, burning at maximum capacity, shedding mass, and nearing the threshold of its final catastrophic explosion. This temporal context adds another layer to its awe-inspiring nature, combining immensity, energy, and impending destruction into a single fleeting phenomenon. The ticking clock of Westerlund 1-26 also provides critical insights for astronomers seeking to understand the life cycles of massive stars. By observing its behavior, including luminosity variations, mass loss, and spectral characteristics, scientists can model the evolution of supergiants and predict the timing and nature of their eventual collapse. Every observation is a window into a fast-forwarded version of stellar evolution, revealing how the most massive stars live and die in compressed timelines that produce dramatic effects on their surroundings. It is a cosmic reminder that, unlike stable stars like the Sun, supergiants are ephemeral titans whose lives, though brief, leave lasting and profound impacts on the universe. Ultimately, the short lifespan of Westerlund 1-26 underscores the paradox of massive stars. They are immensely powerful and influential, yet they exist only briefly on cosmic timescales. Their fleeting existence contrasts sharply with the long, steady life of smaller stars, making them both awe-inspiring and humbling. In just a few million years, Westerlund 1-26 will go from a dominating force of light, energy, and mass to a remnant, likely a black hole or neutron star, leaving behind the elements and energy necessary to seed future generations of stars and planets. The ticking clock of this supergiant reminds us that in the universe, magnitude comes with impermanence, and that the most extraordinary objects are often the most fleeting. The future of Westerlund 1-26 is shrouded in both scientific intrigue and cosmic inevitability. As a red supergiant of extraordinary mass, it is nearing the end of its brief but intense life, and the ultimate fate awaiting it is a collapse so profound that the consequences will ripple across both space and time. Stars like Westerlund 1-26 are destined to end in cataclysmic events, but the aftermath is not merely a spectacular explosion. It is also the birth of one of the universe's most mysterious and formidable objects, a black hole. Unlike stars that fade quietly into white dwarfs, or even slightly smaller supergiants that may form neutron stars, a star of Westerlund 1-26's scale is almost guaranteed to collapse under its own gravity, crushing its core into a point where density becomes infinite and known physics reaches its limits. This is a transformation from a luminous, radiant titan to an invisible, gravitationally dominant entity, a dark remnant whose presence can only be inferred by the effects it imposes on its surroundings. The process of collapse itself is mind-bending. As Westerlund 1-26 exhausts the nuclear fuel in its core, the internal pressure that once counteracted gravity will fail catastrophically. No force can halt the implosion. The core contracts, compressing matter to densities billions of times greater than anything on Earth, while the outer layers are expelled in a supernova explosion that disperses enormous quantities of material and energy into the surrounding interstellar medium. What remains after this violent death is a singularity surrounded by an event horizon, the boundary beyond which nothing, not even light, can escape. This black hole, born from one of the largest stars ever observed, would be immensely massive, perhaps tens of solar masses or more, making it invisible to direct observation and detectable only through the gravitational influence it exerts on nearby objects or by the emission of high-energy radiation from accreting matter. The idea that something so colossal, so energetic in life, can become invisible in death is both humbling and terrifying. A black hole formed from Westerlund 1-26 would possess an extraordinary gravitational pull, capable of capturing nearby matter, gas, or even companion stars in its vicinity. Unlike smaller black holes, which may influence only nearby stellar neighbors, this remnant would be a titanic presence within its cluster, reshaping trajectories and dynamics of the surrounding stars. Its gravity would dominate the local region, silently controlling movements and interactions without emitting a single photon. The transformation from a dazzling, observable supergiant to a completely unseen force is a stark reminder that in the universe, true power is not always visible. Influence can exist in forms entirely imperceptible to the naked eye. The consequences for Westerlund 1 as a whole are significant. In a cluster teeming with massive stars, the death of one star in this manner triggers cascading effects. The ejected material from the supernova enriches the local interstellar medium, seeding nearby gas clouds with heavy elements, while the newly formed black hole exerts immense gravitational influence on its neighbors. Binary systems may be disrupted, stars may be pulled into eccentric orbits, and the cluster's evolution over millions of years is subtly but inexorably altered. In this way, the collapse of a single supergiant is not a solitary event. It is a catalyst for dynamic transformation, both visible in the form of supernova remnants and invisible in the form of a gravitationally dominant black hole. The invisible nature of the black hole also raises profound questions about our understanding of the universe. Though Westerlund 1-26 will vanish from view, its presence will continue to be felt through gravitational interactions, distortions of space-time, and, in some cases, the emission of X-rays and gamma rays as matter is drawn toward its event horizon. For astronomers, this provides both a challenge and an opportunity. How do we study something that cannot be seen, only inferred? By observing the motion of nearby stars, the behavior of surrounding gas, and the remnants of the supernova explosion, scientists can estimate the mass, location, and properties of the black hole. But direct observation remains impossible. The star that once dominated its cluster with light and heat becomes a silent, invisible ruler of its domain, an entity whose true nature is hidden, yet immensely influential. Moreover, the scale of the black hole formed from Westerlund 1-26 would be extraordinary. It would likely surpass the typical stellar mass black holes found in other regions of the galaxy, approaching the upper limits of what we consider possible for individual stellar collapse. Its gravitational pull would be so intense that even photons passing close to its event horizon would be deflected or trapped, bending light and warping the appearance of the cluster in subtle ways. Were this black hole in our own neighborhood, It would silently dominate any nearby planetary systems, reshaping orbits and capturing matter without any visible warning. The concept of an unseen yet overwhelmingly powerful object challenges our perceptions of scale, presence, and the limits of observation in the cosmos. The collapse of Westerlund 1-26 into a black hole also emphasizes the fleeting nature of even the largest and most luminous stars. In just a few million years, a star capable of engulfing planets, emitting billions of times the energy of the Sun, and reshaping its cluster with radiation and winds, will become an entity entirely devoid of light. Its life cycle, from formation to the pinnacle of luminosity and energy output, to violent collapse, serves as a stark illustration of cosmic impermanence. Even the most seemingly dominant celestial objects are temporary, leaving only their remnants and the effects of their death to testify to their existence. Beyond its immediate cluster, a black hole of this scale could also have wider implications for galactic dynamics. Massive black holes formed from supergiants contribute to the population of stellar mass black holes within galaxies, influencing gravitational interactions, star formation, and even the evolution of galactic structures over billions of years. Westerlund 1-26 eventual collapse thus feeds into a broader cosmic ecosystem, linking the death of a single star to the evolution of its cluster, its galaxy, and the universe at large. Its influence, though invisible, continues to be profound, demonstrating that power in the cosmos is not only a matter of size and energy, but also of gravitational dominance and subtle, persistent effect. The invisible future of Westerlund 1-26 invites reflection on the limits of human perception. We are capable of marveling at the star's immense size, luminosity, and energy while it exists. But once it collapses into a black hole, our senses and instruments can only perceive the effects indirectly. This transition from overwhelming visibility to complete invisibility highlights a fundamental truth about the universe. The most powerful phenomena are often beyond direct observation, and the true scale of cosmic forces can remain hidden while reshaping reality around them. Westerlund 1-26 will leave a legacy that is at once awe-inspiring, terrifying, and largely unseen, a silent testament to the extremes of mass, energy, and gravity that the universe can create. Westerlund 1-26 stands as one of the most profound warnings the cosmos can offer. Its sheer size, energy output, and inevitable fate serve as stark reminders that the universe is not a gentle or forgiving place. While humanity often views the night sky as a source of beauty and inspiration, studious observation reveals that the cosmos harbors forces of unimaginable power, forces that can create, sustain, and obliterate on scales far beyond anything we experience on Earth. The existence of Westerlund 1-26, a star so massive and unstable that it could engulf planets and radiate energy billions of times that of our Sun, makes the vulnerability of our own solar system and even life itself strikingly apparent. It is a celestial illustration of how small, fragile, and transient human existence is when compared to the immensity of cosmic phenomena. The star's violent life cycle and impending demise underscore the universe's dual nature as both creator and destroyer. Every aspect of Westerlund 1-26, from its rapid consumption of nuclear fuel to its mass-shedding stellar winds, demonstrates that power in the cosmos is both productive and potentially catastrophic. Its eventual supernova, likely accompanied by gamma-ray bursts and the formation of a massive black hole, will release energy that dwarfs our Sun's total output over billions of years. This is not mere speculation. The physics governing stellar collapse ensures that such catastrophic events occur regularly in the galaxy, reshaping stellar nurseries, triggering new star formation, and occasionally threatening neighboring systems with deadly radiation. The universe does not operate on a scale of safety. It is an arena where the very laws of physics produce extremes that are violent, unpredictable, and unavoidable. Beyond the specific threats posed by its size and potential explosions, Westerlund 1-26 embodies the broader lesson that the universe is filled with hidden dangers. Most massive stars are distant and rare, yet their influence can reach across light years, subtly altering interstellar gas, seeding star-forming regions with heavy elements, and shaping the dynamics of their star clusters. Even without immediate catastrophe, the presence of such stars reminds us that the universe is in constant flux. Gravitational perturbations, radiation pressure, and explosive stellar deaths occur without warning, and the balance that sustains planetary systems like ours is delicate and conditional. Westerlund 1-26, by its very existence, is a monumental demonstration that stability is not guaranteed, that life exists amid forces that are indifferent to its survival, and that the cosmos is a domain of extremes far beyond human scale. The destructive potential of Westerlund 1-26 also forces us to confront the fragility of life and civilization on Earth. While it resides tens of thousands of light years away, the hypothetical scenario of a similar supergiant forming closer to our solar system makes clear how lethal such a star could be. Its gamma-ray bursts, supernova shockwaves, and intense radiation could sterilize planets within hundreds of light years, effectively erasing entire biospheres. The star's extreme conditions serve as a reminder that the safety we take for granted on Earth is a product of chance. The relative distances, sizes, and stability of stars in our local neighborhood, not a fundamental guarantee. In the cosmic theater, Earth is small, and even a single object like Westerlund 1-26, if positioned differently, could rewrite the fate of life itself. Yet, this warning carries a paradoxical lesson. The very forces that make Westerlund 1-26 so destructive are also responsible for creation. Its supernova, catastrophic though it will be, is the mechanism by which heavy elements essential to life are dispersed throughout the galaxy. Oxygen, carbon, iron, and other elements are forged in the cores of massive stars and released in explosive deaths, seeding future generations of stars, planets, and potentially life itself. In this sense, the destructive power of the cosmos is inseparable from its creative capacity. The universe is at once a crucible of annihilation and a womb for rebirth. And Westerlund 1-26 epitomizes this duality. It is both a harbinger of death and a progenitor of the elements necessary for life elsewhere. Observing such a star, even from a safe distance, instills a deep sense of humility. Human perception and civilization are accustomed to thinking in terms of stability and control, yet the universe operates on principles of scale and intensity that dwarf our experience. Westerlund 1-26 is not an exception. It is a rule in extreme form. For every long-lived, stable star like the Sun, there exist massive, volatile stars whose existence is a study in cosmic power and impermanence. They remind us that the universe is not tailored to human comprehension or survival, but rather governed by fundamental forces and processes that produce both beauty and destruction in equal measure. The star's presence is a cosmic cautionary tale, warning that magnitude carries consequences, intensity breeds instability, and the universe operates according to its own laws, indifferent to life or comfort. This warning extends beyond physics into a philosophical reflection on our place in the cosmos. Westerlund 1-26, through its scale, energy, and inevitable death, teaches us that the universe is not centered on life, nor is it constrained by human imagination. It challenges anthropocentric notions of safety, permanence, and significance. Our existence is ephemeral not only because of biological or environmental factors on Earth, but because of the broader, relentless forces of the cosmos, which operate on timescales and magnitudes that render human concerns nearly trivial. Contemplating the star evokes a sense of awe mixed with apprehension. We are witnesses to the extremes of creation and destruction, a civilization momentarily existing in the shadow of unimaginable cosmic power. Even the visual presence of Westerlund 1-26, while tiny and faint to the naked eye from Earth, is a testimony to its immense significance. The photons that reach us are remnants of processes occurring tens of thousands of years ago, traveling across unimaginable distances. Yet they carry information about an object whose scale, mass, and energy are almost impossible to fully comprehend. That we can detect it at all is remarkable, a testament to the precision of human observation and the reach of modern astronomy. Yet even this observation is modest. The real power, the true destruction potential, and the fate that awaits this star are far beyond direct perception, reinforcing the lesson that the universe often operates in ways that are hidden, indirect, and overwhelmingly powerful. Westerlund 1-26 also serves as a metaphorical warning for our approach to the cosmos more broadly. In our pursuit of knowledge, technology, and exploration, we are increasingly interacting with forces that are incomprehensibly vast, from the energy of stars to the dynamics of black holes. Understanding these forces is not merely academic. It is a form of humility, a recognition that even the most advanced civilizations must contend with the sheer scale and unpredictability of the universe. The star's size, energy, and instability remind us that power can exist in forms entirely indifferent to human existence, and that survival on cosmic timescales requires both knowledge and respect for the forces that govern the cosmos. Ultimately, Westerlund 1-26 is a warning from the universe itself, that the cosmos is filled with extremes that can create and destroy, often without notice or predictability. Its incandescent life and inevitable demise serve as a cosmic mirror, reflecting both the fragility and the resilience of life on Earth. While humanity thrives in a comparatively stable corner of the galaxy, this star, and others like it, reminds us that safety is provisional and that magnitude, intensity, and impermanence are fundamental properties of the universe. Westerlund 1-26 is awe-inspiring, not just because of what it is, but because it embodies forces that we cannot control, fully understand, or escape. Its presence teaches respect, instills wonder, and frames our existence as a fleeting moment in a universe capable of both magnificent creation and catastrophic destruction. Westerlund 1-26 stands as one of the most awe-inspiring monuments in the cosmos, a testament to the unimaginable power, scale, and creativity of the universe. Even from tens of thousands of light years away, its presence commands respect, challenging our very understanding of size, energy, and time. To consider a star capable of engulfing entire planets, radiating billions of times the energy of our Sun, and ultimately collapsing into an invisible, gravitationally dominant black hole, is to confront the extremes of reality itself. It is a reminder that the universe is not bound by human imagination or perception. It operates on scales that dwarf our comprehension, where energy and mass reach levels so extraordinary that they inspire both terror and wonder. The enormity of Westerlund 1-26 defies ordinary description, yet its existence is tangible, measurable, and profoundly impactful, offering a direct connection to the forces that govern cosmic evolution. Every aspect of this star, from its colossal size, which could swallow Earth and extend beyond Jupiter, to its rapid consumption of fuel and catastrophic instability, embodies extremes. Westerlund 1-26 demonstrates that stars are not mere pinpoints of light in the night sky, but living dynamic entities capable of reshaping their surroundings, distributing essential elements for the next generation of stars and planets, and reminding us of the fragility of life in the universe. It exemplifies the paradox of cosmic creation, a star so destructive that it could obliterate entire solar systems, yet so generative that it produces the very elements required for life elsewhere. Its life, though short, is a powerful narrative of intensity, impermanence, and influence on the galaxy at large. The eventual fate of Westerlund 1-26, its collapse into a black hole or neutron star, underscores the silent, invisible power that persists even after a star's light has faded. It will continue to shape its stellar neighborhood through gravity, influencing the motion of nearby stars, guiding the formation of new stellar bodies, and serving as a testament to the transformative cycles that govern the universe. The star reminds us that the most profound forces often exist beyond direct perception, yet their effects ripple through space and time in ways that are far-reaching and significant. It is a humbling reminder that the cosmos is not only vast, but also filled with objects whose power can be felt indirectly, long after the light from their violent processes has traveled across galaxies. In contemplating Westerlund 1-26, we are reminded of our own smallness in the vast expanse of the universe. Our Sun, which sustains life on Earth, is tiny in comparison, its energy output and lifespan modest against the overwhelming scale and intensity of a supergiant. Yet, within that smallness lies perspective. We exist in a universe capable of producing extremes so vast and powerful that they challenge not only our comprehension, but also our place within the cosmos. Westerlund 1-26 exemplifies the sublime tension between creation and destruction, between beauty and terror, and between the fleeting human experience and the enduring, relentless processes of the universe. To witness the existence of such a star, even from a distance of 14,000 to 16,000 light-years, is to feel the immensity of cosmic time and space. Westerlund 1-26 demonstrates that in the grand scale of the universe, magnitude is not measured solely by size or brightness, but by influence, energy, and the capacity to alter everything within its reach. Its life, death, and invisible aftermath embody the cycle of stellar evolution in its most extreme form, a narrative of creation, domination, and transformation that dwarfs human scales and lifespans. It is both terrifying and magnificent, a cosmic reminder that the universe operates on rules and scales that extend far beyond our daily experiences. Ultimately, Westerlund 1-26 is more than a star. It is a lesson, a warning, and a spectacle all in one. It teaches humility in the face of scale, patience in understanding cosmic processes, and awe in observing the raw power that the universe can marshal. It is a star that dominates space, not merely through size, but through the sheer extremity of its existence, radiating energy, shaping its environment, and reminding all who study it that the universe can create objects whose magnitude challenges comprehension, whose power can both destroy and create, and whose very presence humbles even the most imaginative human mind. The final awe comes not just from imagining its size or energy, but from realizing the profound truth it represents: that the universe is capable of producing extremes so vast, so intense, and so transformational that they dwarf all human constructs and understanding. Westerlund 1-26 is a cosmic giant, a living furnace, a harbinger of both creation and annihilation, and a silent, invisible ruler of its domain in the future. It is a star that commands respect, instills wonder, and above all, reminds us of the grandeur and terror of the universe. A force that humbles our very existence and challenges the limits of our imagination. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.